Hi, my name is Dweej Patel. My project is detecting cancer from medical images. The major ideas and concepts implemented in this project come from the paper Detecting Cancer Metastasis on Gigapixel Pathology Images. The process in this project is first extract the data, then balance that data, create a model, then train the model, and show the predicted heat map. Now I'll be going through the code walkthrough since it provides a comprehensive overview of the project. So here is my project, Detecting Cancer from Medical Images. Here I install the required libraries. Then I go on to mount my Google Drive, and from my drive I unzip the slides folder to my Colab disk. The reason why I unzip the Colab disk is because read speeds are much faster on Colab than if I were to read those slides from my drive. Here, I just label the slides and masks and put them in a directory to make it easier for me to refer to any one of the files later on in the code. Here, I show slide 91 as an example of how the slides generally look like. Here are the dimensions of each level. Here is the slide at zoom level 5. Here is the tumor mask at zoom level 5. Here is the overlay of the mask and the slide. And here is the tissue pixels, the pixels which are important to us. Now here is the data extraction portion. Here are some helper functions to help me with data extraction. The first function, get and check images, will extract images in a tissue if they are found, meaning that we first read from the slide for a particular window, and if that particular window contains a specified amount of tissue, so a certain percentage of tissue above a threshold, then I return the image. Else I don't return the image, and I return none. The reason behind choosing a threshold on percent of tissue is because let's say you have a scenario where you have 1 pixel that's a tissue in the entire image, and the rest of it is gray, and we don't care about that image. So choosing a threshold allows us to pick an ideal situation where we choose the right amount of tissue within each image. I further go on to create a helper function to extract the mask and say if that particular window is cancerous or not. I do that by simply putting a threshold on the cancerous region as well. So if the mask contains enough cancerous region, then I return that the entire image is a cancerous region. Else I return a 0, meaning non-cancerous. Here is a helper function to help me correctly place each of the images into a correct directory structure. Slide to dir is an important helper function which passes a window through the slide. Here I'm passing the window through the slide. I get and check the image. If the image is not none, meaning that the image is of interest to us, then we pass it to check mask, which returns if the area of interest to us is cancerous or not. Then with that information, we can put that data into our specified directory structure. Now here is where I pass all the parameters to my helper functions. First, I create a validation set. Then I create my training set. Here for my validation set, I use slide number 91. And for my training set, I use slides 78 and 110. The reason why I use slides 78 and 110 is because they have a pretty even distribution of non-cancerous versus cancerous cells. Also, note here that I'm using level 0 to extract the images. Now, once the images are extracted, I look at the data. Here we can see that we have 613 cancerous images for the validation set and 8,717 images for the non-cancerous cells. And the same goes for the training set. We have 24,173 images for the cancerous and 36,731 images for the non-cancerous. So as we can see, this data is highly unbalanced. And to balance the data, I simply randomize the file list. Then I choose a cutoff point for each of the validation sets, for each of the validation and training set for the non-cancerous images. And I simply remove those files. And then doing a sanity check again on the data, we see that the data now is pretty even. We have 613 for cancerous images on the validation set, and we have 813 non-cancerous images on the validation set. And the same goes for the training set. Here are some of the images in our validation set that are cancerous. Here are certain images that we extracted that are non-cancerous. Here I'm creating the datasets. I'm creating datasets using image dataset from directory. Here my validation dataset and test dataset are the same. I use an Inception v3 architecture to create my model. My base model is Inception v3. Here, as you can see, the weights are set to none. We set the weights to none and not ImageNet because ImageNet is a vastly different image set than the image set we have currently, which is cancer cells, or cancer tissues, I mean. Here, we use a global average layer and a prediction layer, which gives us a binary classification. Here, I used code to increase performance for my dataset in terms of it being cached and prefetched. But since we're working with data set at level 0. We cannot use this because our RAM is maxed out. So here it's commented out since I'm using level 0. Here I fit my model, and as we can see that we're getting 92.5% accuracy in our validation set. Here I'm plotting the accuracy of our validation set versus the training set. As we can see, we're getting a pretty good validation accuracy. Here I'm getting slide 75, which I will be creating the heat map for. Here is how 75 looks. Here I'm creating the actual heat map for slide number 75. And then here I'm overlaying that heat map with the slide itself. As we can see, we have a pretty accurate prediction of a cancerous region here and a cancerous region here. And here I'm showing the ground truth heat map. As you can see again, that the tumor region is shown to be here and here mainly. But going back here, we see that we have some areas of inaccuracies around this area right here. We're predicting inaccurately that it is a tumor, but it's not. And there are a few specks here which are not really noticeable, which are inaccurately being predicted also. But overall, I would say that the ground truth and the predicted mask match pretty well. To conclude this, I would say that we have a very good match, and to increase the accuracy, I would use more data and use different zoom levels